All right, so we will go ahead and get started. I'm sharing my screen. There's a document which I can share afterwards. This document, it's just a pointer to some resources. Of course, our main resource about NHDPlus high-res is the web page, which is linked right there at the top. And there's a new-ish web page that we developed called the value-added attributes of the VAAs, which I'll show you in just a moment. But all the material you're going to see today is on this GitHub site, which is this link right here in the center. If you search for GitHub, ACWI, and NHDPlus HR, you should be able to find that. So all the materials are there. This is from a workshop that we gave this past summer at the Quasi Hydroinformatics workshop or Hydroinformatics conference at the end of July. So this is that GitHub page that you will find from that link. And all the materials are right here under the documents. There's a VAA workshop. And so the presentation that I'm going to go through here in just a moment and the exercise that Mike will be showing in a few minutes are here, and some other information, including that resources document that I was just showing. It's all here on this GitHub page. So with that, I'm just going to start with a quick presentation. Sorry, hang on, that's the wrong slide. Start at the beginning. Okay, again, this was from the Hydroinformatics conference in July. So here's what I'm going to cover. I'm going to do a very, very quick overview of hydro data sets and NHDPlus concepts and high-res NHDPlus. I hope that that's review for almost everyone on this call. And I'm going to try to really focus on that value-added attributes and talk about those. After that, Karen's going to do a quick demonstration of using a tool called the VAA Navigator. And just a second, what I'm going to do is I'm going to mute everyone because there's a little bit of background noise. And so I've muted everybody, and I'm going to unmute our two speakers, which are Karen and Mike Basile. So hang on. Okay. Karen, can you say something just so I know we've got you? Well, we'll deal with that when we need to switch. I'm not
hearing. Can you hear me?
Yes, I can hear you, Karen.
Okay.
And then Mike is going to go through, at the end, Mike is going to go through a tutorial of how to do VAA navigation. So we're burning time here, so I want to move right along. So, you know, basically, you all know about NHD, WBD, and NHDPlus, I think. Hopefully, everybody's kind of aware of the three major data sets that we manage in the hydrography program with USGS National Geospatial Program. You know, we have flow direction as part of NHD, and you can do navigation in the NHD itself using a geometric network. In ArcGIS desktop, ArcMap. Just a preview, there will be some additional functionality coming in ArcGIS Pro. It's not there yet, but we've been talking with Esri about that, and you'll be able to do this sort of thing in ArcGIS Pro probably within a year. But what we're going to talk about today really is how to do navigation on the NHD network using a set of value-added attributes, and we'll go through those. So you'll be able to do this with attributes and very simple queries. You won't have to have those geometric networks or the new trace network that Esri is developing. All right, so what's NHDPlus? It's a combination of these three data sets, the NHD, the WBD, and the 3-depth elevation data. I'm not going to dwell on this. I think everybody hopefully knows the difference between NHDPlus version 2 and high resolution NHDPlus. Just briefly, version 2 was developed, versions 1 and 2 were developed off of the 1 to 100,000 scale NHD at the same time that NHD itself was being updated to 24,000 or better. And so now we're building the high-res NHDPlus on that high-resolution data set. We're adding all of these attributes and this additional functionality that was built in NHDPlus to the high-resolution data. So the concepts that I'll be talking about with value-added attributes apply both to the medium-resolution NHDPlus, either version 1 or 2, and also to the high-resolution NHDPlus. The big thing that NHDPlus brings in is catchments, but it also has rasters for flow direction, flow accumulation, and several other raster data sets. But the main thing is the catchment area for each stream. That lets us link landscape processes to the stream network. And then just a few samples of applications that have been built on NHDPlus medium res. The Sparrow model is a water quality model. Lets you understand where nutrients are coming from on the landscape. There's this tool called Icy Water, which is a incident command spill response type tool that lets you compute time of travel in the stream network. This is a desktop tool that the Defense Threat Reduction Agency supports for emergency management organizations, and it's in place in a lot of emergency management centers around the country. It runs in desktop ArcGIS, and it works off of NHDPlus medium res version 2. The National Water Model is being run down at the National Water Center in Tuscaloosa. Actually, it runs on a supercomputer, I think in NCAR in Colorado, but the Water Center in Tuscaloosa is the main outlet for it. And then, so that's all, again, based on NHDPlus version 2. Eventually, they hope to port that over onto the high-res NHDPlus. So there's some tools built into something called the Water Quality Network, or Water Quality Portal, sorry, that use these query-based attribute search to do upstream and downstream traces. And that's the basis. Those services are the basis of some of these slides that I'm going to show you here, where you can use these. These are web-based services where you can navigate upstream main stem, upstream with tributaries, downstream with divergences, and this is a zoomed-in view showing you all the divergent paths going downstream, or you can do downstream main stem as well. So these are some services that currently exist. They're built on NHDPlus version 2. It's all query-based network navigation. So that's the main thing that these applications that I was just showing is that they are based on attribute queries. And there's more information at these websites. Again, these links in this presentation is all available on that GitHub site. So NHDPlus high-res, I didn't have a chance to update this status map, but these areas in California and the lower Mississippi are done now. We're now focusing on the Great Lakes region, Region 4. So we plan to finish that during this fiscal year, hopefully. And then we'll be finished with all of CONUS. We also have done some work in Alaska, and we're working on Hawaii right now as well. And then there's a markup application. We've talked about that on this call before that lets you report errors, problems with it, either with NHDPlus or with the basic component NHD or WBD datasets. And then this is just a view of the vector geodatabase that you get in NHDPlus high-res. And there's several pieces of this that I'm just going to kind of move over real quickly. There's raster datasets as well. The one that most people would be interested in would be the flow direction grid. There's also flow accumulation and several other raster datasets. Okay, so the main topic here for today is these value-added attributes. So it's there's this set of attributes that are built. They're built in a completely automated process, and it produces a whole bunch of attributes. And these attributes really are designed to help make analysis easier and network type analysis, network trace upstream and downstream type traces easier and more powerful. So this is a list of the value-added attributes. Several of these, there are some that are kind of popular, like stream order. And I'm not going to go through every single one of these, but I will go through several of them, and then I'll also point you to a web page where there's more information about each of these attributes, value-added attributes. So the first one is just it's called Strahler stream order. It's just kind of a surrogate for stream size, and it's been a very popular one. Basically, a first-order stream is a headwater. You get a second-order stream where two first-order streams come together. You get a third order where two second-order streams come together, and then so on, going down. You only increment the order when you meet, going downstream when you come to a confluence of another of the same order, another stream of the same order. So stream order is there. There is a set of from and to nodes that are nationally unique identifiers for those nodes at the endpoints of each of the flow lines. This is used because a lot of models use kind of a node-linked navigation system. The one quirk to this is that there is no actual node feature class. It's not a geospatial feature class. It's just these numbers are attributes in the table for the lines as the from and to nodes. So the values are in the line tables on the flow line, NHD flow line. So another attribute is called path length, and that's the distance from the downstream end of a segment or a flow line to the end of the network, which for most networks is at the coast. So every flow line knows the length from its downstream node to the end of the network, and that's called path length. So another really important VAA is called the hydrosequence number. And so this is a nationally unique set of numbers. It's a sequential number that puts the flow lines in hydrologic sequence. So basically, low numbers are at the end of the network at the coast, and then you go to higher numbers going upstream. So it's if you sort all of the features in the data set in ascending order, you'll go from downstream to upstream, or if you sort them in descending order, you go upstream to downstream. So you can be guaranteed, for example, if you sort them descendingly and process through. So let's say you want to accumulate some kind of attribute like percent forested area. If you do that by accumulating and processing the data in descending hydrosequence order, then you'll always be guaranteed that if you're sitting here somewhere on the network, you're guaranteed that you will have processed all the records upstream, and all you need to do is just add them up. So it makes it easy to go through and process the data set sort of in one pass. So it makes it much more efficient for building accumulation type models. So another attribute is called stream level. And so basically stream level is, it starts with level 1 at the coast. And what you do is we go upstream from the coast, and at every confluence we choose which is the main path. And the level stays the same along that main path, basically following the main path all the way up to the headwaters. So that's a level 1 path, is this one that's in blue here. A level 2 paths are ones that drain to a level 1, and then level 3 paths are ones that drain to level 2 paths. And so this basically gives you the ability to identify a single stream all the way from its mouth to its headwater. And so there's another attribute called level path identifier. And what that is each of those level paths that I showed on the previous slide, let me back up, each of them gets an identifier, and it's the identifier, basically, it's the hydrosequence number of its most downstream segment. So that hydrosequence number of this stream segment here would be the level path ID for this level path. It goes up like that. So by choosing all the flow lines with a particular level path, you can get that river main stem. So for example, what we've highlighted here, I believe, is the Susquehanna River, where it enters into the bay going out into the Atlantic. And so that's the main stem of the Susquehanna all the way to its headwater. Very quick and easy query. There's another ID called the terminal path ID, and that is basically the hydrosequence number for the last flow line in the network. So the one we just saw with the Susquehanna would have remember, it has a hydrosequence number, and the level path ID that has that hydrosequence number is the main stem going up. But if we look at terminal path ID, every flow line in that watershed, everything upstream of this, is going to have the terminal path ID of that last segment in the stream network. So the one we're seeing here is the end of the Mississippi in the Gulf of Mexico. And so the hydrosequence number of that flow line is going to be in the terminal path ID field of every flow line in the Mississippi River Basin. Every flow line that's connected to the outlet of the Mississippi River. So that makes it very easy to find the entire watershed of a drainage network that drains to the ocean, for example. This one, again, is the Susquehanna, and the flow line that drains it is somewhere down here in in the south. So basically, we just, with one query, we select all the flow lines that have that terminal path ID that is the end of the Susquehanna, and we get the entire, all the flow lines in that watershed, in that drainage basin. Another attribute that we have is total upstream drainage area. So that's been accumulated and computed in there. And so what here I'm showing is just a few selected attributes on a flow line. And so we have the hydro sequence number of the flow line itself. We have its terminal path ID, or level path ID, sorry, and its terminal path ID. And we have this total drainage area in square kilometers. So every flow line has its upstream total drainage area. Okay, so NHD is not a completely dendritic stream network. It has many divergences in it. So there's a attribute called divergence code, which basically tells us which are the major flow paths out of a divergence and which are the minor flow paths. So whenever you come to a divergence, like we're coming down this stream, if it's the major path is going this way, the minor path would be these red flow lines. And the software has a set of rules that it uses to determine which one is the major path and which is the minor path going downstream. So if we want to get a dendritic network, it's a simple query to just remove all the minor paths. And that query, there's an attribute called stream calculator, which is explained in more detail on the web page. But to select and get a dendritic network from NHDPlus, all you have to do is do this simple select stream order for equals stream calc, and that will give you a completely dendritic network selected. So it's very powerful and very fast, easy thing to do. Okay, so how do we put this all together? So here's a level path ID, and in this case we're up in Alaska looking at the Susitna River. We choose, again, just like we did with the Susquehanna earlier, we choose all of the flow lines that have the level path ID that equals the end of the Susitna River where it enters the ocean. Then if we want to find the watershed upstream, or all of the flow lines rather upstream of that last flow line where it enters the ocean, then we select on terminal path ID for everything that has that same hydrosequence number, that same number. And then we can add it all up. We can add up the arbolate sum, which is the upstream cumulative drainage, or upstream cumulative kilometers of stream network. So it's the length of all the flow lines, NHD flow lines upstream. So we can get that. We can also total up the drainage area that's associated with each of those stream flow lines. So all of the catchment areas, and that's what we get, how we get the total upstream drainage area. And then, so here's another example where we're doing something with two of these attributes. There's an attribute for elevation on each flow line. There's a minimum and a maximum elevation of each flow line, so it's the bottom and top end of each flow line. If we plot that minimum elevation versus the path length, which, if you remember, that was the distance down to the end of the network, then we get this longitudinal profile of that level path. So that's a very quick and convenient, easy thing to do, get a longitudinal profile. And we can even do all the longitudinal profiles of all of the level paths in a watershed really easily. So lots of cool things that you can do with these value-added attributes. Okay, so here again, just to wrap up these resources, there's this VAA webpage, which I'll show you in just a moment. We have a user guide. It's coming very, very soon. I know I've been saying this for a couple years now, but it is really, it's basically at the printers right now, virtual printers. We won't be printing paper of this, but the PDF will be available really soon. In the meantime, the NHDPlus version 2 user guide is a good reference for kind of the concepts behind all of this. Again, that all these materials that you'll see today are at this GitHub repository, and then, of course, see our web page. All right, and I think that is the end of that. That's just our emails. Myself, Karen Adkins, and Mike Basile will be presenting today. So, and then I did just want to show you that VAA webpage. This is linked off of our main webpage, and it's got little write-ups on each of these value-added attributes and little diagrams to show you what they're all about. So it's a good reference there. Okay, so Karen, are you ready to do your demonstration?
Yep, I sure am.
Okay, take it away.
Hey, I've just got a couple of slides I want to run through real quick. This is the VAA Navigator, the NHDPlus High Resolution VAA Navigator that I'm going to be demonstrating. It uses the value-added attributes to perform the network navigation, and you can navigate on any NHDPlus HRGA database as a single hydrologic unit or append them together and perform navigation. It comes with an ArcMap toolbar, but there's also modules that you can call from code. And the benefit of that is that you can navigate multiple hydrologic units and drainage areas without having to append them. So the toolbar is pretty simple, very easy to see. You have upstream or up main stem navigation. You can navigate upstream with tributaries. You can navigate downstream and downstream with tributaries. And there's also a little salt shaker, I think it is, to delete the working database. So move forward. And when you are navigating, your options, you do have options. The database path, you do need to have a SQL database that you have access to, so you do need to have read-write access to the directory that you're telling the database to go to. And you can start from the bottom of the feature, or you can start at any reach code measure. You can also set distances to stop, so you can navigate the entire network, or you can navigate only to a specified distance. And there's also filters that you can apply using different attributes and operators to control your navigation. So you can navigate based on path length, arbolet sum, the total upstream cumulative drainage area, that's tote VA square kilometers, and the div VA square kilometers, that's the divergence routed cumulative drainage area at the downstream end of the feature. So I am going to go ahead and bring over my ArcMap session. And just keep in mind right now that the Navigator is built for ArcGIS 10.5.1. That's what I'm demonstrating in today. but that code is available through the GitHub repository that Al provided in the link just a couple minutes ago. So this is the toolbar. Once you have a NHD flowline loaded from an NHDPlus high-resolution data set, you do want to make sure that you join the data based on the NHDPlus ID to the NHDPlus flowline VAA table. And I've already joined that. And when you do start a network navigation, you want to make sure that you're starting from that where you are clicking, you actually have to highlight the NHDPlus flowline. If you don't have the flowline highlighted and you try to do a navigation, it'll tell you that no flowline is active. So you do want to make sure that you have your flowline activated. To perform a simple navigation, you can just drop a point anywhere you want to. I'm going to start at the bottom of, I believe, what is the Kentucky River. So I'm going to start at the bottom and just perform a simple navigation. It'll take a moment the first time that you run the Navigator, but it goes pretty and it will add the navigation results to your ArcMap session. So you can see that that is navigating all through that flow line, that network, all the way up to the top. Now, it's not picking up on any of the tributaries. So if you want the tributaries, you do need to redo your navigation with tributaries. And so if we do the same navigation with tributaries, but you don't want to do the entire flow line, you can just control it to 10 kilometers, and you'll get results that will pick up on the tributaries. Okay, so that's up to 10 kilometers distance, so you can see that it's only going to that specified distance. So keep that in mind when you're using it. If it might cut off some of those upper reaches if you are specifying a distance. So, and while my session is drawing, so if you do want to perform a navigation using one of the filters, again, need to make sure that my flow line is active. So you do want to start at a particular location, and you do want to use a filter. You can use one of these attributes to filter your results. I'm going to use the div VA square kilometers, and the operators that you have are greater than or less than or equal to, greater than or equal to, and greater than. I'm going to try less than or equal to. And this does require you to kind of know the data, understand what it is you're looking for. It'll give you the right results. So you can perform those navigation upstream or downstream. Just be familiar with the data and what it is you're looking for. So everything there has a div VA square kilometers less than or equal to 1340 kilometers. So it's reaching all along that segment. So, and then you can always clear the working database if you need to. You can clear that working database. And it is just a simple ArcMap toolbar, so you just add that tool through your customization of your tool menu. And it's taking its time. Okay, it's unable to drop, so it's still in use. So, so that's basically it. It's a pretty simple tool to use, but again, just be familiar with your data. Make sure you understand the data before you start navigating, but it is really interesting to use, and you can play around with that and get some really interesting results. So again, I mentioned that you can call the modules. There's 3 classes or modules: the load SQL Server database, and the make working table, and the VO3 Navigator. So the first one loads your flow line VAA, the plus flow, negative data into a single working database. And then making the working table, it creates that for a single navigation from the data that's loaded into load SQL Server DB. And then the Navigator itself, that module calls the Navigator and puts the results in that SQL Server table. And that's everything I have.
Okay. Thanks, Karen. I'll just real quickly, there was a question in the chat about whether it only works with the SQL database. So the software itself creates a little SQL Server, I think, SQL Server database that it uses, that it does the querying on. The data themselves are in an Esri geodatabase that's being used here. And again, this is code that works just in ArcMap right now, but the code is there on GitHub. So if you're a developer, you would be able to take that and make it work in whatever environment you want it to. And then Mike Basile is going to follow next. And so, Mike, maybe you could start sharing your screen and getting ready while I explain a little bit more how this all relates. So Mike's going to show how the actual logic works in these queries that Karen was just showing, the upstream, main stem, upstream with tributaries, and so on. So he's going to show the logic in how you do that, and he's actually going to demonstrate all of that in ArcGIS Pro, and he's also got a small little Python tool that he built that he's going to show that's also on that GitHub repository. So, Mike, are you ready to share your screen?
Yeah, can you not see it yet?
We're seeing the grid of all of the participants on the call. I think maybe we're seeing a wrong screen.
Let's see. There we go. How's that?
I see it.
You see it? It hasn't shown up on mine yet, but go ahead, Mike.
Okay. So this workshop, and I'll see how much I can get through in the next 15 or so. I have till the end of the hour out, correct?
Yeah.
Okay. So this was originally put together for a desktop version, and since there's been quite a bit of transition into Pro, I felt it would be useful to move some of this into an ArcGIS Pro platform. And so many of these queries don't function the same way in desktop. So just be aware of that if you do decide to download this from the GitHub site and look at some of it yourself. So I am going to start by going through some of the workshop and how to do it, and then I'll actually just skip through some of the redundant stuff to just show you results of what the output ends up looking like. But the initial upstream main stem navigation is relatively easy, and it really just comes down to identifying what the level path ID is of the river that you're looking to navigate up. And then in this case, it's the Patuxent River, and it has this level path ID. Yeah.
So sorry, Mike, I'm still not seeing your screen. Is anyone else seeing what I'm seeing? It says it's sharing. I'm seeing your screen, but what I'm seeing is the WebEx participants view. Like
I can see Mike's screen.
I can see Mike's screen.
Oh, okay. Go ahead, Mike. Mine must just be behind.
Okay.
Sorry.
Yeah. Well, luckily you've seen it before.
Yeah, I have.
And so in this case, this highlighted level path ID is the level path ID of the Patuxent River. And so if I come over to my pro session here, and there's so many little windows, all right, and I run that selection, you can see that from the point where it enters the Chesapeake Bay up to this headwater feature right here, all share the same level path ID. And so that way we can see right away where we're going to be working in isolating the tributaries that all flow into the Patuxent River, which is going to be the second portion of this. So upstream main stem, relatively easy. We built a VAA that does just that. The next part of this navigation workshop is to find all of the tributaries that are flowing into the Patuxent River. And to do that manually, it's an iterative process that involves some embedded selection queries, select by attribute queries. And the first step to this is just to export the level path ID that we just selected to its own layer. And we'll then be working with two separate layers to make that happen. And so I like to create geodatabases to work out of because mainly that's what Esri supports. And by using the geodatabases, these embedded queries actually work a little bit better. If you're trying to work out of just file folder pathways, a lot of these queries will not work. So just keep that in mind. So now if I turn off my all of my flow line layers, you can see that I've exported just that level path ID layer. Now what I want to do is step back real quick and show you something that I did beforehand that takes a little bit of time. So Al showed you the file trees for all of these, and you can see that you get, all of these layers with the high-res download. So what I did initially before I started talking to you was I joined the NHD Flowline feature class, which has my physical features, with the NHDPlus Flowline VAA layer right here. This is the table that contains all of our VAAs that we've assigned to each individual flowline feature. And the way that those are joined is through the NHDPlus ID attribute, which is contained in both the NHD Flowline layer as well as this NHDPlus Flowline VAA table. So just so that we're clear, that's how I'm getting all of these VAAs attached to my actual physical features. So what's next is now that I have my nav results 1 and my NHD Flowline VAA layer both in the same geodatabase, I can use one of my embedded queries. And so what this is doing is it's looking for any of the records whose down level path, which is the down level path identifier VAA value that is also located in the level path ID field of that initial nav results layer that I just exported. But then it's also looking at the hydro sequence attribute. So it's also taking the down minor hydro sequence value that is located in that VAA layer and picking out if it has a corresponding hydro sequence from that nav results layer. And you'll see what happens first, and then it'll become very clear why this is an iterative process. And so, make sure that all looks good. Great. So I'm going to zoom in here so we can see a little bit better. So our initial selection was all of the features that ran up through the Patuxent River. And what you see is that we've now gained all of the tributaries, or not all, but many of the tributaries that, sorry, I apologize. It is all of the initial tributaries that are flowing in. You have to just zoom in a little bit closer to see some of these detailed areas. And so what ends up happening when we do this is every single time I export this new selection to another layer, And then I run this query again just with my updated nav result. So I like to just know where I am. So I would name this new exported layer nav result 2. For the interest of time, what I'm going to show you is the final output. And everything that I'm doing is described and easily walked through in this document that's on the GitHub. What ends up happening is you end up with an exported layer. In this case, it's called nav results 9. And it means that it took 9 iterations for me to capture the whole section of stream here, the whole watershed that is connected to the Patuxent River. And the way that you know that you've hit the final amount of iterations is that the exported layer, so this nav results 9, if I were to run nav results 9 again, I would get a nav results 10 layer. The number of features between those two layers would be the same. And if those feature counts aren't increasing anymore, you know that you've hit all of the features that are selectable in that watershed connected to that river. And so you end up with this watershed, and you can even follow along the boundaries here, and you can see, oh, there's clear breaks where everything that is to the right of my cursor is flowing to the right, and everything to the left of my cursor is flowing to the left. So those are two of the manual ways to pick out or find all of the inflowing features to a watershed. But if you'd like to maybe pick out just the tributaries to a certain river, the workflow is a little bit different. So I'm going to walk you through just the initial navigation workflow to pick out the tributaries of, in this example, the Patapsco River. And hopefully this works for me because I already have it lined up, and we should be able to pan to this portion. So what I want to show here first is when we identify this feature, we can see it's the Patapsco River, and it has a level path ID of this long number here. So one of the questions I tend to get is why would we not just select by the named feature? Why are we using this level path identifier? And I'll show you that real quick. And the reasoning for that is they do slightly different things. And I'm going to start just by showing you initially what happens if I select just by the GNS ID of the Patapsco River. I'll just throw this one in manually real quick for everyone. And if I zoom to that selection, right, I see where the final feature of the Patapsco flows into the Chesapeake, and then I can see where that named feature ends. But clearly there's quite a bit more upstream connection here. And so the reason why we use level path ID is it actually gives you the main path all the way up to a headwater. And right there you can see we gained a lot more stream. And if you go to the top, you can see that it starts somewhere at a headwater. Right now, we still are working on getting another attribute called main path that would potentially change the main path to here. But for now, our level path ID runs through up to this headwater. Okay. So I have built a query here that will show us all of the named tributaries to the Patapsco River. All right, so basically what this query is saying in English instead of SQL is that it's going to select any flow line features whose immediate downstream flow line is the Patapsco River and whose downstream hydrosequence VAA is greater than or equal to the minimum hydro sequence on the Patapsco. And if you remember from Al, when he was talking about hydro sequence, that it shows or that it works in that descending order. And so you're able to use the less than, greater than, or equal than selection style to actually pick out your named features. And you can see right now, we found all 21 features that are named, or another explanation for that is they're larger streams because they have a name that are your inflows into the larger Patapsco River. I do have a secondary query here that you can add if you are interested in gaining all of the inflows to the Patapsco, and I've set it up that we're just going to add it to this selection. And you can see we've jumped from 21 up to 77, and now we've picked up all of the unnamed tributaries as well. So just to take a little bit further, and from there, this is what you can then use to do further analysis if you're trying to figure out, you know, how much flow you have coming into a particular stream river. You can utilize all of these selected features to see what they contain upstream from your main stem that you're looking at. Because I don't think I have enough time, I am going to move past the last little bit of navigation. And it basically is just a way to determine how many lakes are along the Choptank River. And then you can also use our VAAs to determine how far the mouth of each of those lakes is from each other, as well as how far the mouth of each of those lakes are from the main outflow into the Chesapeake Bay along that river. But I'll leave that one up to you all to try on your own if you're so interested. I believe, Al, I saw some questions popping up as I was going through this, but I don't know how to access those.
I think I've answered the ones that have showed up in the chat, but we do have about 5 minutes here. So I just unmuted everybody, I think. Unmute all. So if anyone has questions, you can just speak up right now. I think I've been unmuting everybody. There we go. I can hear people. Any questions for any of us?
Al, there's a series of questions in the chat.
Okay, I've been trying to follow those. Sorry, I'm not seeing any others. Can somebody read one if there's a question I haven't answered yet? And actually, Mike, let me just share my screen again, just to point out those web pages again. Wow. Okay, so this is the GitHub page. Again, all the documents for this workshop are under the docs folder, the VAA workshop folder. So this, the materials that we just went through are all here. This is the VAA webpage, on our webpage. This is our NHDPlus high-res webpage, which is easy to find. And if the VAAs, there's a link to that VAA webpage right under the map there. This is our current status map on that webpage. Anything else anybody has? Any questions?
Hi, Al. This is Sarah Rosa from Pacific Islands Water Science Center. I'm just wondering if eventually you guys will expand to Guam or Puerto Rico?
Yes, if we have the areas where we do have NHD data right now, we are planning to work on. So we've started work on Hawaii right now. That's in the work here, and now Guam, I can't recall whether there's NHD data for it. But the rest of the islands, the island territories, Puerto Rico and the Pacific Island territories, where we have NHD, we plan to ultimately produce NHDPlus high-res. And I believe that's on our plan to do this fiscal year, but it's going to fall kind of later in the fiscal year, and it will also depend on other priorities. So it's possible it could get bumped off, but it is in the plan.
And Al, this is Drew. There is a new NHD for Guam. So. Okay.
Yeah. So it would be included. So that's Region 22, I believe it's called. And so wherever we do have NHD data, planning to produce those NHDPlus.
Thank you.
Any other questions? Okay. Well, thanks everybody for coming.